Hey guys, we're going to take a look at the periodic table again and just review all of the information that we've talked about. So without further ado, let's dive right in. The first thing that we need to do is we need to go through and label our groups and our periods. So on the far left-hand side, I'm going to number these 1 through 7. Okay, and these right here, these are all of my periods. So everything going down the side right here are periods. Going the columns across the top, all of these are my groups. Okay, and my groups are numbered 1 through 18. Now that I have all of my periods in my groups, we can delve a little bit further into the periodic table. First thing that I'm going to do is I'm going to start working on the staircase where my metalloids are located. So the staircase is just this area in between metals and non-metals that help me identify at a glance which elements are metalloids. So starting at group 13, and working your way down all the way over one block at a time to group 16. The key thing right here is that you're just darkening this line. You don't want to make it too thick to cover up all of the information, but you definitely want it to be noticeable. And so now this part of the periodic table is going to stand out a lot more than the rest. Now you're going to need 3 different colors. And you're going to use these 3 different colors to identify which elements are metals, nonmetals, and metalloids. We're not going to color in the entire thing like we did last time. We're just going to outline. But I still need a key at the bottom so I know which color represents what section. Okay, so there are my different colors. And I'm going to say that this kind of dark blue purple is going to be my metals. The yellow is going to be my metalloids. And the green is going to be my nonmetals. Now I can go in on the periodic table and start outlining each of the boxes. I'm going to start with the metalloids because those are the ones that are hardest to identify and they help separate the other 2 sections. So I'm just going to outline all of these boxes that are a part of the metalloid section. This is just a reminder that metalloids have properties of both metals and nonmetals. They act frequently as semiconductors, meaning that they can partially conduct heat and electricity. Okay, those are all my metalloids, and I no longer need this color, so I'm going to set it off to the side. I'm going to do the metals next because they're the largest section. They take up the majority of all of our elements. And so with the exception of period 1, group 1, hydrogen, everything in groups 1 and 2, all the way through everything in group 12, all of these are classified as a metal. Metals, if you remember, are really good conductors of heat and electricity. This is one of the reasons why they are used for construction, as well as different wires. Copper especially is probably one of the most commonly used items for wires. Iron is the second most abundant element in the Earth's crust, which is one of the reasons why we use it so frequently. There is only one metal that is a liquid at room temperature. All of the other metals are going to be a solid at room temperature. That one metal that's a liquid is mercury, number 80. So here I have all my main group elements highlighted or outlined. And now I'm going to get the inner transition metals down here, because these are technically metals as well. Alrighty, that takes care of all of my metals, so I'm done with that color. And onto my final color to highlight or outline my non-metals. So just a reminder, hydrogen is the Lone Ranger. He's all over here by himself in group 1, but he is still classified as a non-metal. And then everything past my metalloids, these are all non-metals as well. Alrighty, now that we have all of where our basic sections are, we can go through and we can start naming these. I do want to separate a couple of sections to make it easier. So right here at group 3, I'm going to put a dashed line. Group 3 is to help separate where I want this section at. Same thing over in group 12. Just going to put a little dashed line going down to help separate this middle section here. I'm also going to draw 2 arrows from group 3, period 6. So group 3, period 6, and period 7, I'm going to have a couple of lines coming down to the 2 rows at the bottom. Okay, and what this indicates is that these 2 rows right here technically fit in to those 2 little blocks right there. But for the sake of being able to fit it all on one piece of paper, we decided to put it at the bottom. So now let's go through and name these. So group 1 are the alkali metals. Okay, the alkali metals are the most reactive of all of the metal groups. Group 2 are the alkaline earth metals. So the alkaline earth metals are reactive, but not near as much as group 1. Groups 3 through 12, all of the elements that are in this section are the transition metals. So groups 3 through 12 are the transition metals. Inside the transition metals, we have what are known as the inner transition metals because, you know, they're inside. So the inner transition metals have the lactinide series, or lanthanide series, combine the two names. So start off with the lanthanide series on top. And then I have the actinide series on the bottom row. Next, I'm going to move to my nonmetals, mainly group 17 and group 18. Group 17 is known as my halogens. Group 17 is the most reactive of the nonmetals. Meanwhile, group 18, the noble gases, are the most non-reactive. They don't want to interact with anybody. All right, whenever you are looking at the periodic table, you are going to see that each box has some different components. So we're going to draw a box representing what we would find in each block on the periodic table. Okay, so when you look at a normal periodic table, you're going to see a number up at the top. You're going to see one or two large letters. You'll see a name. And then you'll see some more numbers at the bottom. All right, and each one of these represents something different. So we're going to go through and we're going to label each of these. So the number at the top is the atomic number. And we've talked about before how the atomic number is equal to the number of protons. That is what defines what my element is. The large letter or two that you see in the middle is the chemical symbol. And then underneath the chemical symbol, you have the chemical name. Your chemical symbol will forever and always have one capital letter. This is extremely important because every time you see a capital letter, that means that there is a new element. If you have a lowercase letter, it's going to be attached to a capital letter. So here I have Na for sodium. If I had just N by itself, then that would be nitrogen. Those are two completely different elements and they act very differently. That's why it's extremely important to know the difference between a capital letter and a lowercase letter. Before we move on, there is one thing up here that I would like to recap, and that is the charges on my protons, neutrons, and electrons. Your number of protons will always give you a positive charge. Protons are positive. Neutrons are neutral. They have no charge whatsoever. And electrons have a negative charge. Please be extremely careful. A lot of people, not everybody, a lot of people are getting the charges mixed up, so you need to be extremely careful. Protons are positive, neutrons are neutral, and electrons are negative. And we can use these three things to determine other factors. So, for example, we mentioned earlier that the atomic number is the same as the number of protons. Okay, and then, oh, I forgot one. I do apologize. The number at the bottom, I got ahead of myself. So the number at the bottom of a box is the atomic weight. Please keep in mind that the atomic weight is different than the atomic mass or the mass number. The atomic weight is going to be the number that you derive or that you get directly from the periodic table. The mass number is something that you will need to calculate, and it's mainly used to calculate neutrons, because your mass number minus the atomic number is equal to your number of neutrons. We can rearrange this formula, so if I am looking for neutrons, this is a really handy formula equation. If I'm looking for the mass number instead, I can say that protons plus neutrons are equal to the mass number. And the last thing that I can use protons, neutrons, and electrons for is to calculate the charge. So I can take my number of protons and I can subtract my number of electrons to calculate the charge. So I'm gonna take a moment and just separate these out just for ease of access. My brain works better when I separate some things, so I'm just gonna draw a line. Not super important, just something that I like to do. While we're talking about all of this, we can also go ahead and look at the isotopic notation for something. So the isotopic notation is when I have two numbers that are stacked on top of each other next to a chemical symbol, and then sometimes I'll have another number up at the top. So we're going to identify what each of these mean. So the first number that is stacked on top is the mass number. So on the top left-hand side, that's going to be your mass number anytime you see isotopic notation. The atomic number is the number on the bottom left. My giant letters in the middle, we mentioned earlier, are the chemical symbol. And then lastly, my tiny number that is either going to be positive or negative is my charge. When I'm looking at the periodic table, if I am looking at the group, if I am looking at the group number, I can determine the number of valence electrons. My number of valence electrons is determined by the electrons in the outermost shell. When I'm talking about shells, I'm talking about the energy levels. So we know that an atom has the nucleus in the center, and then it has a bunch of rings around it. The number of rings, or the number of energy levels, is determined by my period. So if I'm looking at group 1, all of the elements in group 1 are only going to have one valence electron. And I'm going to label these as VE for valence electron. All of the elements in group 2 are going to have 2 valence electrons. When it comes to my transition metals, groups 3 through 12, they act really funny, and so we're gonna ignore those. When it comes to valence electrons, it can vary and it changes, so we're gonna ignore them. We're gonna jump over to group 13, where I can have 3 valence electrons. Group 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18 has 8. These are my total number of valence electrons. My valence electrons can move around. Sometimes an element wants to gain or lose electrons. But the key thing is that every single element on the periodic table wants to be just like my noble gases here in group 18. This is because your valence shell can only hold 8 valence electrons, the maximum, with the exception of period 1 where it can only hold 2. So because every element wants to gain or lose electrons to achieve that magical number 8, we end up with charges. And so your charges are referred to as the oxidation number. I'm going to use ON to represent that. So if I'm looking at group 1 that only has 1 valence electron, it's more likely to lose that electron than it is to gain. So if I lose 1 valence electron, I am left with a +1 charge. Group 2 is going to lose 2 electrons, so it has a +2 charge. We said we were skipping the transition metals, so jumping to group 13 with 3 valence electrons, we'll have a +3 charge. Group 14 is special. I can either gain or lose 4 electrons. So group 14, I can either lose and end up with a positive charge, or I can gain and end up with a negative charge. It can act as both. Group 15 has 5 valence electrons. Therefore, they want to gain 3. And when I gain 3 electrons, I gain 3 negative charges. Group 16 wants to get 2. Group 17 wants to gain 1. And we mentioned earlier that group 18 is perfectly stable, so they don't want to gain or lose any electrons whatsoever. This covers everything on the front page regarding the periodic table itself. So what we're gonna do is we're gonna flip over our piece of paper. In my case, I'm gonna get a new one because I used markers and we can see that it left some residue. And so you guys are gonna flip and do it on the back page. Going over some key concepts, primarily the Bohr model, ions, and isotopes. So we're gonna start with the Bohr model. Whenever we're looking at a Bohr model, we have the nucleus. Okay, and your nucleus consists of protons and of neutrons. And the nucleus is extremely tiny and very separated from the energy levels. So I'm doing a dotted line so that we don't confuse our nucleus for our energy levels. And so energy levels are going to hold the electrons, and each ring, each energy level, can hold a certain amount. So we're gonna draw this. There's our first energy level. Here's the second energy level. And here's the third. Now, technically speaking, because there are 7 periods on the periodic table, I could have up to 7 rings, but I will not be quizzing or testing you guys on that, so we're not going to focus on it too much. So when I'm looking at the first energy level, the first energy level is only going to hold up to 2 electrons. And that's because when you look at your periodic table, I'm gonna bring this back real quick. When you look at your periodic table, period 1 only has 2 elements in it. So if I only have 2 elements, I can only hold 2 electrons. Then it starts to fill the second energy level, and this one can hold up to 8 electrons. And if you were to count on period 2, there are 8 different elements. And so you're gonna stop wherever you need to. And then the third one, yes, there are only 8 elements in period 3, but like I said, the transition metals act a little funny, and so this is where that comes into play. So the third energy level is going to hold up to 18 electrons. And like I said, beyond this, I'm not going to ask you guys anything. So let's practice an example. Let's say that I have sulfur 33. Just a quick reminder that this number right here is the mass number. Whenever you're given the element with a number next to it, that is the mass number. So that tells me for this particular sulfur atom that we are going to be drawing, it's going to have a mass of 33. So if I were to look at my periodic table, you guys would look at your green one, you would find that sulfur is in group 16 in period 3. So group 16 in period 3, and I can do kind of like a little target right here. And so you would see that sulfur is atomic number 16, which means I'm going to have 16 protons in my nucleus. I also have neutrons in my nucleus. So what I'm going to do is I'm going to take a different color so that we don't get confused. I'm going to take the mass of 33 minus 16, and I'm going to do some math so that we find out that we get 17 neutrons. You guys will have a calculator available to you on the test, so do not worry about that. Alrighty, so I'm gonna circle my nucleus. Alrighty, and we mentioned earlier that it is in group 16 in period 3. We said that periods determine my number of energy levels. And so since it's in period 3, I am going to draw 3 rings. So I have my 3 rings for my 3 periods. Now, this is a neutral atom. I have no indication that this is a charge. So we're gonna say that this has 16 electrons in total. I need to divide these 16 electrons up between my different energy levels. So my first ring, we said, can only hold 2 electrons. And so I'm going to draw like a little arrow. This is the first level for that number 2 right there. So I have 2 electrons going on my first energy level. The second energy level can only hold 8. So 16 minus 2 leaves me with 14 electrons. We said that the second energy level can only hold a maximum of 8 electrons. And so then 14 minus 8 will leave me with 6 electrons. There's 1, 2, 3, 4, 5, 6, 7, and 8. It doesn't really matter how far or where your electrons go on the Bohr model. The key thing is that because all electrons have a negative charge, negative will repel negative. So they're going to push each other away as much as possible. So that's why I'm drawing them opposite of each other first. And so if you notice, we are left with 6 electrons, which coincidentally, I am using the wrong color. there we go, are our valence electrons. Because sulfur is in group 16, it has 6 valence electrons. And so these numbers are always going to work out very nicely. So I'm going to put my 6 valence electrons. And that is how we can draw and identify a Bohr model. And all of that information I just took from the periodic table. Now, I'm going to section this off so that we can talk about some other stuff. So going back to our example earlier with sulfur 33, the mass number is something that can change, and that's what gives me an isotope. So for example, I could have sulfur 32 instead. It's the same element, and chemically speaking, they're gonna act alike, but they're still different because the mass number right here is different. So when my element is the same and my mass number is different, or when my protons are the same and my neutrons are different, I have what is called an isotope. So these two atoms of sulfur 32 and sulfur 33 are isotopes of each other. Using this same example, I'm going to write this in isotopic notation. We'll use sulfur 32 this time. So you might have noticed there's something a little different. On this one, on the bottom, I have a -2 charge, but on the first one, I don't have a charge at all. So anytime I have a charge where I have an atom or atoms that's the same element, but different charges, those are known as ions. Something to remember with ions is that you have 2 different types. The first one is cations, will always have a positive charge. So anytime I have a +1, +2, +3, or +4 charge is going to be a cation. Anions are going to have a negative charge. So anytime I have a -1, -2, -3, -4, those are all anions. And remember, we get a positive charge by losing electrons, and we get a negative charge by gaining electrons. And that goes back to protons being positive and electrons being negative. So cations are going to have more protons than electrons. Anions are going to have more electrons than they're going to have more electrons than protons. And that covers everything from the periodic table and a few extra things that are going to be on the test.